Hello and welcome back to Nunley Math. I'm your host, Aaron Nunley. Thank you so much for joining me as we continue our discussion of functions and specifically graphs of functions. We're working our way through the different types of functions that we're responsible for in Algebra 1 and even a couple that, that we are not necessarily responsible for but that will be helpful and interesting and useful to us. I've already done two types of functions. We've introduced the linear function, which always makes a straight line, and we've also introduced the absolute value function that we said always makes a v. And we've talked about the fact that we're not interested today in the most efficient way to graph a function. Rather, we are looking at doing this the long way, the hard way, in order to find some patterns so that we can do them more efficiently in the future. So, without further delay, let's talk about this one. F of x equals x squared minus 5. I'm going to create some items in my domain. I'm going to check to see if they work in my function, and then I'm going to see what the output is. We'll list those as a coordinate, and we will graph those looking for patterns along the way. Once again, I would encourage you to take a second, pause the video, plug in some points on your own, see if you can get this graph, and then start the video and see what I've done, and we'll have a discussion about what we see. I'm going to start with just some easy numbers. I usually use 0, 1, 2, 3. When I'm first starting out, I also like to use -1, -2, and -3. Here again, you can use any numbers you want. You want to try and find things that fit on your coordinate plane, though. This is going to be f of 0 equals 0 squared minus 5, which is -5. And I'm going to graph that. As I stated in the other videos, I'm not going to write f of every single time. Instead, I'm just going to go ahead and do the function part over here, 1 squared minus 5. That'll save us a little bit of time, keep this video from getting too long and too out of hand. If I plug in a 2, I get -1. If I plug in a 3, I get 4. If I plug in a -1, I get 1 minus 5, which is -4, which I'm going to graph here. I am going to pause for just a second. Make sure if you plug a negative value in for x that you put that negative value in parentheses. Keep in mind that all of x gets squared and the negative sign is part of your answer. Some people may be wondering, why does that make such a difference? Well, when I do -2 squared minus 5, over here in the margin, -2 squared is -2 times -2, which is +4 minus 5 is -1. But if I had not put this in parentheses, it actually says something quite different. It says take a negative sign and do 2 times 2, which is -4. Notice that without the parentheses, you only have one negative sign, whereas with the parentheses, you have two negative signs. It does change your answer. -3 squared minus 5 is 4, which is here. And did I do the -2, -1 yet? I did not. I've got some extra room. Let's go ahead and do 4 squared minus 5 and get 11. And let's do -4 squared minus 5 and also get 11. And that's right here, and it is right here. Do you notice anything interesting or useful about that particular graph? Hopefully, you realize that it does have a lot in common with the absolute value function, in that one side is in fact a mirror image of the other. I'm going to go ahead and draw my line of symmetry here. This is my line of symmetry. Once again, it is on the y-axis. They are not always on the y-axis. There's your equation for the y-axis. Notice as well that unlike the absolute value function, this is not two straight lines. Instead, this is two curves. Two curves. which looks like this. Now, because I could see the pattern, I'm making the assumption that everything in between will also work. I can test that if I want. If I put in 1/2 squared is 1/4. 1/4 minus 5 is -4 3/4, which is right here. Those do fit on here. I'm also making the assumption that as I continue on and on and on, it is going to continue to grow as opposed to come back down. And that's a pretty safe assumption, especially if I look closely at the patterns that emerge. Notice here I went up 1, up 3, up 5, up 7. Here I went up 1, up 3, up 5, up 7. So knowing that, I can pretty well assume that this is going to go +9, +11, on and on and on. There again, that's a very interesting pattern that tends to emerge from quadratic functions. We'll talk about that more a little further down the road. I did just say what this is. This is a quadratic function. The graphs of all quadratic functions will look like this. They will all make parabolas. Parabolas. Or in adjective form, we would say they would be parabolic. Parabolas and parabolic. Every quadratic function is going to make this same basic shape. Now, as I stated with absolute value, they could be tall and skinny. They could be really, really wide. They could be upside down. I could move this whole graph to the left or to the right or to the top or to the bottom, but it will always make that same basic shape. It'll just move around just a little bit and widen and narrow. We'll talk about how to change that shape a little bit further down the road, but for now we just want to get a good idea of what a quadratic function looks like in very general terms. Once again, notice that just like the absolute value function, this does have a vertex, a spot that the line does approach. It reaches that, and then it changes what it's doing. That vertex happens to be a minimum because it is the lowest point that my graph ever reaches. I should go ahead and list that coordinate as 0, -5. And that coordinate also happens to be my y-intercept. Again, it will not always be the y-intercept, but in this case, it happens to be. We've talked about the line of symmetry. The line of symmetry always goes through that vertex. We've talked about the y-intercept. Let's look at the x-intercept. The x-intercept is where it crosses the x-axis, and hopefully you've already realized that this actually has two x-intercepts. It crosses the x-axis in two places. Notice also those are going to be decimal places and not integer values. This is going to be a number between 2 and 3. This one is going to be a number that's between -2 and -3. So finding those is not going to be as simple as just looking at the picture. What I do know is that whatever coordinate that is, it is going to be something, 0. Whatever coordinate this is, it will be something, 0, because the first value tells me how far left and right to go, the second value in the coordinate tells me how far up and down to go, and this doesn't go up or down from the origin at all. Since I know my f of x is 0, I can take my function, f of x equals x squared minus 5, and I can just ask myself, what would make that f of x into a 0? This is an equation I can solve. How do I get rid of -5? Add 5. How do I get rid of squares? Well, we've learned along the way that we can get rid of things by using the inverse operation, or doing the opposite. That's why to get rid of -5, I did +5. To get rid of times 3, I divide by 3. To get rid of a square, I'm going to do the opposite, which is the square root. It is important to keep in mind that when you are doing square roots, you do end up with two answers. 3 squared is 9. -3 is also 9. So when I do square roots, I need to make sure I get both the positive and the negative answer. Because of this, I'm going to make that into positive -5. This is, in fact, x equals plus or minus radical 5. You do have a key on your calculator where you can do the square root of 5. For the sake of our video today, I'm just going to leave it as radical 5 and negative radical 5. the square root of 5 is a decimal between 2 and 3. It's about 2.1-ish, I'm thinking. Actually, probably closer to 2.3-ish. But there again, for now, the exact answer is better than us having to give a decimal that we round off. Lastly, our domain and range. Domain is which x values will work. As we look at our table, you will notice that every x value worked. And if you look at our arrows, we can see that as I'm going to the left, it looks as though it's going to continue to the left forever. As I go to the right, it looks as though it's going to go to the right forever. So my domain is all x as long as x is a real number. For my range, I'm looking at where the graph goes up and down, or what the output values will be. You can see I got a series of output values here. I can't really see the pattern there, but I can see it here in the picture. If I start at my vertex and go to the right, I'm going up forever. If I start at my vertex and I go to the left, I can see it's going to go up forever. What that tells me is there is no limit to how high this graph can go. But I do notice that as I'm going down, after I reach -5, the graph changes directions and turns back up. It's never going to go below that -5. So it's going to be greater than or equal to -5. Any idea why it turns around at -5? Well, look what's happening here. -4 squared is 16. -3 squared is 9. -2 squared is 4. -1 squared is 1. 0 squared is 0. But then when I get to the positives, 0 squared is 0. 1 squared is 1. 2 squared is 4. 3 squared is 9. -1 squared and 1 squared both have the same positive answer. 2 squared and -2 squared both have the same positive answer. No matter what I stick in here, it's always either going to be 0 squared is 0, or it's going to be a number with a positive answer. Because of that, 0 minus 5 is -5. A positive number minus 5 is always going to be higher than that. There's nothing I can add to this, or I can take 5 away from, that will give me a lower solution unless this is negative. -2 minus 5 would get me down here to -7, but there's no way to get a -2 because all squared values are going to be non-negative. Very helpful to us as we look down the road. Again, this is not the best way. It's not the most efficient way, but it did reveal for us some things that are going to be helpful for us as we look at these in the future. Keep in mind, once you know the type of function and the shape of the function, it will help you eliminate a lot of the work you need to do in the table. As always, thank you so much for joining us today. If this was useful to you, please make sure you leave me a comment in the comment section. Take time to like and subscribe and turn on your notifications so you can follow along with us as we work our way through functions. Thank you so much. Best of luck to you. Take care.